This is lecture 7, part 3, and in this particular part, I'm going to focus on preliminary assessment techniques as applied to the set of peaks that have the highest M to Z values. So presumably what you would think to be the molecular ion as it passes through the mass spec analyzer. Just to review from parts 1 and 2, we're going to focus on molecules containing C, H, N, and O, and we have the isotope distributions, namely carbon being an A+1 element, having a carbon-13 with 1.1 abundance, nitrogen also being an A+1 having a 0.4 abundance at MZ15, and oxygen being an A+2 element having a isotope satellite 2 units away, 18, having a 0.2% abundance. Finally, hydrogen being an A element, and for analytical purposes, the deuterium and tritium abundances are so low you don't see them in conventional mass spectra. In part 2, we learned how to count the number of atoms of a given elemental type using the isotope lines as the means to do the counting. And we were reminded by our boss that we have to be a little wary of the imperfect nature of mass spectrometry, the errors involved, and so on. So with this particular set of data in mind, and this is actually from the SDBS database, I'll reveal its identity shortly, but we see that we've got some issues immediately. So these are the highest M to Z values in the mass spectrum, and we have two very large peaks, and they can't possibly correspond to isotope peaks. So the 105 and 106 corresponds to no isotope pairing or isotope satellite lines in the molecules that we're discussing. So this is inconsistent with what we know about these elements. So we have to ask ourselves which one of these is the molecular ion passing through, or the principal peak, and which are the isotope satellite lines. So since 105 can't be, because 106 corresponds to no isotopic abundance for any of the elements that we're looking at, that means that 106 has to be A. And 107 will be A+1, and 108 will be A+2. Having made that assignment now, we look at the A+1 value, and we see that we would naively, given a 1.1 abundance per carbon, we would suspect that the best value is a 7 carbons. So 7 carbons are best. We have a range, however, given the errors that we've imposed, of 7.0 to 8.6, and we have to acknowledge that. So when we incorporate the error bounds, we have to at least think along the lines of the possibilities existing, namely 6 to 8 carbons in the molecule, and then we have to kind of rule some of these out. When we look at the A+2 and apply the error bounds, it looks as though we have an A+2 range with the error of 0.3 to 0.7. Looking at the abundance absolute, we would say that 2 oxygens is the best fit. However, with the A+2 error bounds, we have to consider everything from 1 to 3 oxygens being a possibility. So the error involved, substantially changes the number of guesses that we're going to be working with when we try to interpret the mass spectrum. So we're considering a molecule that has something between 6 to 8 carbons and 1 to 3 oxygens in it. And the question raised by the boss is what can we attribute the 105 peak to? And the boss's big sister comes in and says that hydrogen abstraction is the likely culprit. So it's probable that the molecule is unstable in the beam and is losing a hydrogen. So this is the actual molecule involved. This hydrogen is labile. It tends to get torn off in the electron beam when the molecule is ionized. You see that it does have 7 carbons and 1 oxygen, so it was a very good representation in the mass spec. And the fact that you see a 1-to-1, roughly 1-to-1 relationship between the 105 and 106 peaks means that you're probably about getting half of the benzaldehydes stripped of their hydrogens and going through the analyzer. So we learned something about this, namely that the odd-numbered M to Z values suggest a molecular fragment, namely a broken molecule. And the way we can rationalize this, which we'll do in the next slide, is that most of the elements that we're dealing with in these organic molecules have combinations of valence and atomic weight, namely odd-even relationships. So if you have 2 evens, you get an even-valued M to Z, namely valence, even valence, and even atomic weight gives you an even M to Z. 2 odds likewise give you a even value, and we'll see what I'm talking about shortly. And then an odd and an even combine to give you an odd. So we'll start to see why this is so in the next slide. So I'll illustrate this using a generic formula for a hydrocarbon to start with. So the formula for generic hydrocarbon that is saturated is CnH2n+2. You learn this in organic chemistry. If I calculate the M to Z value of the parent ion, the molecular ion that goes through the analyzer, the M to Z value is going to be n times 12 plus 2n plus 2 times 1 for the hydrogen contribution. And that's always going to be even valued for all possible n's because I'm always multiplying by 2. So when I start to have unsaturation, in other words, I make double bonds and triple bonds, for each degree of unsaturation, I have to remove 2 hydrogens. So I'm always going to retain that even valued M to Z as a result. If I start looking at other functional groups now, I can examine oxygen. And when I add oxygen as a double bound oxygen atom, I have to remove 2 hydrogens from the carbon center. So that also retains the evenness because I'm removing 2 hydrogens with each additional carbonyl-like functional group. If I do a single bonded oxygen, I'm taking away 1 hydrogen, but I'm also putting that back on, namely on the other side of the oxygen for an alcohol group. So I'm always maintaining the balance with oxygen and the evenness. However, if I now start working with nitrogen, which is trivalent, there are 3 scenarios. A single bond takes away 1 hydrogen and adds 2 on the nitrogen, which gives me a net gain of 1, which is odd. Double bond, I take away 2 hydrogens and add 1 hydrogen back, so I'm still odd. And then the triple bond takes away 3 hydrogens, giving me a net loss of 3 hydrogens, which is an odd scenario. So when I have an even number of nitrogen, so that's when I have an odd number of nitrogens attached to the carbon skeleton. If I have an even number of nitrogens on the carbon skeleton, the 2 odds created by each of the nitrogens essentially become an even. So if I have an even number of nitrogens on the carbon skeleton, I get the even valued M to Z back for the parent ion. So diamine is a typical example. So let's look at a couple of case studies. The first of these is dimethylamine. So this is the structure on the upper left. If I count up all the atomic weights for this molecule, I expect a M to Z of 45 for the molecular ion coming through the analyzer. The mass spectrum for the molecule is in the center of the slide, and when I get the table of abundances, I see that I have the following somewhat messy looking thing, and the expected M to Z, namely the 45, is not the most abundant species, but as Domino would tell us, these are likely hydrogen abstractions involving removal of the proton from the amine or the methyl groups. The A+1, if I look at that, it's inconsistent with what I would expect. It's about twice the value I would really expect for a 2-carbon compound. And it's probable, since it's one AMU higher, that somewhere in the analyzer there's chemistry taking place, and I'm getting a little bit of dimethylamine formed with an added proton on the nitrogen. If I look at the ethers, and this is one I discussed in class, lecture, the structure of the molecule is given in the upper left-hand corner. Again, I expect a parent ion to come through with an MZ of 74. When I look at the spectra, I see that the 74 peak is not the most abundant peak in the mass spectrum. In fact, the most abundant is at 31, which means the molecule is getting beat up. But if you think about it, that's like one of the ethyl fragments coming through with a proton attached, or 2 protons attached to it. So chemistry is taking place. The molecule is getting beat up in the beam, and I'm not getting, so the ether bond is getting beat up in the beam, and the molecule is fragile. So to analyze this and to make some sense out of the mass spec and use it to determine what the molecule was, I need to normalize the peak that I'm calling A. So again, if I look at this, there's no isotope combination that looks like this. So I'm stuck with calling 74 the A. It's my best choice in this matter. If I'm going to analyze the A+1, namely the 75 and 76 peaks, the A+2, I need to scale up 74 to 100 and use that scaling factor and apply that scaling factor to the A+1 and the A+2 peaks. So I want an X such that X times 43.7 gives me 100, and that calculates to be 2.29. And I'm going to multiply this times 74, 75, and 76 and get the following. When I apply the error bounds, I get 5.3 plus or minus 0.5, and I get 0.2 plus or minus 0.2. So my guess is my best fit is 4, and I'm not given much leeway, carbons, 4, maybe 5 carbons in the structure, and 1 or 2 oxygens in the structure. And that's how I would interpret this as a starting point. So in conclusion of part 3, and here reviewing the preliminary assessment of mass spectra, you always go to the mass spectra approach and locate the peaks with the highest M to Z values, and you try to ask yourself, is this the parent or the molecular ion with a set of isotope satellites, namely an A+1, and A+2. Upon identifying the A, you ask yourself, is it odd valued, in which case it's either a molecular ion with an odd number of nitrogen atoms, or it's a fragment. And when we start talking about fragments, all those peaks to the left of the highest M to Z, you'll see that most of those are odd valued. And then finally, if the A peak doesn't have an abundance of 100, you have to scale it up accordingly and apply that scaling factor to the A+1 and the A+2 to actually apply the isotope satellite rules and do the counting for the molecule. Okay. And that concludes part 3. These are the bibliographic references, and you will find much of this in the Blackboard notes for the course. So I encourage you to look at those Blackboard notes and work through the examples.